Okay, I hope you can see the screen also.
Yes, sir.
Okay. So in the last class, we talked basically two very important topics which were important relations, which are one need to use it various problems. That is we talked about fundamental equations, 4 different fundamental equations based on internal energy, enthalpy, Gibbs energy and Helmholtz energy changes. And from there, we also derived 4 Maxwell relations. Okay. And I told you why it is so important, those Maxwell relations, because you can easily convert into measurable expressions where you can measure quantities like in terms of the parameters that are present in the equation of state. Okay. Now today we will see a few things where we'll be using those fundamental equations and Maxwell relations, how they are used in problems, okay, or certain derivations. Now let us start with this. What is we are going to derive some equation called thermodynamic equations of state. Now we start from this fundamental equation. This fundamental equation concerning the internal energy change. So du equal to TdS minus VdV. We know that. Okay. Now from there, so here you see that so your internal energy depends on entropy and volume change. So if I take a derivative with respect to volume at constant temperature, okay, then you have this expression T del S del V at constant T minus P. Okay. Now you see, now we have an opportunity to apply Maxwell relations, because I told you that entropy calculations or finding out these changes with respect to volume, pressure, temperature is difficult task. So therefore, Maxwell relations help us so that del S del V at constant temperature T, if you look at that yesterday what we discussed, is equal to del P del T at constant V. Okay. So that means entropy change with volume at constant temperature. If we, instead of that, if we measure how pressure and changes with temperature at constant volume V, it will give you the exactly same picture. Okay. So now it is easy because we know equation of state connecting P, T and V. So therefore, if we keep volume constant, and then we can very easily calculate how pressure changes with temperature. Okay. So that is the reason why Maxwell relations are so useful. So we write down this expression. Now we know this cyclic rule. From there, what we are trying to get is we are trying to get an expression of these. So del P del T, we are converting it into this term. So del P del T can be written like this minus, you see that, so this term comes to the denominator del V del P, and this one I am taking in the numerator by reversing the derivatives, taking the reciprocal of it. Okay, so it becomes minus del V del T at constant P. Now there is a reason of writing this, because these two are important quantities which can be actually measured also, both experimentally as well as can be calculated from the equation of state. These are known as one is this alpha, which is the expansion coefficient, and another one is the kappa, which is the isothermal compressibility. So what is expansion coefficient? As the name shows, this is a measure of expansion contraction of your system. It says how volume changes with temperature at constant pressure, and then you normalize by total volume. So it's a per unit volume. Okay. So you know, if you increase the temperature, then system volume increases. Okay. So therefore, this is called expansion coefficient. Okay. Rate of change of volume with temperature per unit volume. Okay. This is a quantity known as alpha. Then this one is known as compressibility. This is a measure of how compressible is your system. Okay. Because you see, it tells you the change in volume with respect to pressure. Okay. You know, if you increase pressure, volume decreases, or if you decrease pressure, volume increases. They have an inverse relationship among themselves. So therefore, therefore there is a negative sign. Okay. So there is a negative sign. So how volume changes with pressure at a particular keeping the temperature constant, and then you normalize per unit volume. Okay. So this gives you the compressibility of the system, how compressible it is in nature. So at constant temperatures, we call it isothermal compressibility. Now, since these are measurable quantities, we are converting this into that. So that's why reason why we wrote this expression. Okay. Now this one we substitute in this first equation. So we get an expression of this one del U del V at constant temperature is T alpha by kappa minus P. Okay. Or you write it down like this. Now this expression is known as the thermodynamic equation of state. Okay. Now in normal, equation of state, pressure, volume, temperature. That pressure is the kinetic pressure of the gas. Now this is also a pressure. Okay, if you take the dimension of this, energy by volume, that gives you a dimension of pressure. So this is therefore known as the internal pressure or some thermodynamic pressure often. Okay. Now where from it comes? So this basically tells you how internal energy changes with your volume. So internal energy means essentially kinetic plus potential energy, the total energy of the system. Okay. Now this depends on intermolecular interactions, because what happens if you change the volume? If you change the volume, then basically the intermolecular separation between the particle changes. You have a system containing many particles, molecules. Suppose you have a gas or liquid or whatever it is, they are present in a system. Now, if you change the volume, then actually the distance between the particle will now change. So if the distance between the particle will change, that will immediately change your say potential energy. Okay, so that will change your potential energy of the system. So therefore, this is called as the internal pressure, which arises due to your interaction between the particles. Okay, so that's why we call it as a thermodynamic equation of state, because it involves one of the thermodynamic parameter, internal energy. Now, from very easily you can find out if you take ideal gas. If you take ideal gas and you find out this alpha expression, say from PV equal to RT, ideal gas expression, if you find out alpha, you will see alpha will be 1 by T, and similarly kappa, this compressibility will become 1 by P. Okay. Now, if you use these two, put it down the expression here, then you will see del U del V at constant temperature equal to 0, which is nothing but the result that Joule got from his experiment. Okay. So this leads to the Joule's experiment result for ideal gas. Okay. Now, if you take a non-ideal gas, then this term will be non-negative, non-zero. So therefore, del U del V will be non-zero. Okay. Now, in a similar expression, I have not done the detailed derivation, but you can do it yourself. So I tell you to do that yourself. You can get a similar expression for enthalpy also. Okay, del H del P at constant temperature. Okay, this is connected with this V into 1 minus alpha into T. Okay, now which expression you will start? To get H, you will start from the corresponding your fundamental equation. Okay, that is dH equal to TdS plus VdP. Here we started with du, TdS minus PdV. For enthalpy, the corresponding equation is dH equal to TdS plus VdP. Okay, but then exactly in the same manner, you take a derivative and then you will be applying a Maxwell relation, corresponding Maxwell relations, and you can very easily derive this expression. Okay, so this is a kind of similar type of expression, but here this dimension, if you see that right hand side dimension is actually volume. So this is enthalpy by pressure. Okay, that means basically energy by pressure. So if you write the energy by pressure, that becomes simply a dimension of volume. Okay, so this tells you the volume. Okay, this contains the volume of the expression. If you take alpha into T, that is also basically a numberless quantity, a unitless quantity. Okay, because alpha is this one. So alpha into T, if you do this, basically it becomes a unitless. Okay, so therefore this is corresponding similar type of expression for involving enthalpy. And again, if you take ideal gas, very easily you can show that del H del V at constant T equal to 0. Again, this is from Joule's result for ideal gas. Okay. So this is again first example where you can use these fundamental equations and Maxwell relations, and you can derive this type of important equations. Next, there are a couple of these are very important. How Gibbs energy is a very important quantity. Probably out of all the thermodynamic quantities, Gibbs energy change is the most important one, because it tells you about the spontaneity of a process. Okay, we will very soon derive an expression for how you will know whether a process is spontaneous or not, depending on the delta G value. the change in Gibbs energy for a process. Okay. So therefore, it is important how this Gibbs energy changes with a temperature change or pressure change. Okay, Gibbs energy or the Gibbs energy change for a process. Okay, what is the effect of temperature and pressure on that? Now, since we want to know Gibbs energy change, you see that our starting point is the corresponding fundamental equation. In the previous two cases, say we started with internal energy and enthalpy, those two fundamental equations. Now this is here we are applying another fundamental equation that involves Gibbs energy. Okay, so dg equal to vdp minus sdt. This was the fundamental equation. This is the starting point. Now if you take a look at that expression, you see it depends on pressure and temperature. Okay, that means you can know, looking at the expression, that your Gibbs energy will depend for a system or for a process. The corresponding change will depend on the temperature and pressure. Okay, so we'll see now the temperature dependence first. Okay, now we want to see temperature dependence, so I take a derivative of this with respect to temperature. Okay, if I write with respect to temperature at constant pressure, then this becomes minus S. Okay, entropy. Now again, entropy we need to convert it, because entropy is cannot be computed very easily. So what we do now, we start from the definition of G equal to H minus Ts. Okay, and now this entropy expression we write like this, and from here I get the del G del T at constant P expression in terms of G minus H by T. Okay, basically the entropy we have replaced by this. Okay, G minus H by T. Now we can write it down in a different ways. Suppose we take a derivative like this, G by T del T. You know the simple derivative rules. So you can find out that that will be minus G by T square. If I take the derivative with respect to T, and then another one is 1 by T into del G del T at constant P. I'm simply applying the product rule, G into 1 by T. Okay, in that product rule, if I apply, I get this derivative. Okay, now the second term, already we know this is actually G minus H by T. So in there is a T denominator, so it becomes G minus H by T square. Okay, if you sum it up, you get minus H by T square. So what we are getting this expression, how G by T with the derivative with respect to temperature gives us minus H by T square. Now H by T square I can write in the differential form like this, because you know derivative of 1 by T will be minus 1 by T square. Okay, so therefore this expression I can write an equivalent expression like this. Okay, because I wanted to bring similar type of differential on both sides. Okay, so from here, therefore I can now do a rearrangement, so I can bring this del 1 by T on this side, so it becomes H. Okay, so del T by T by del 1 by T equal to H. Yes.
Sir, you have written minus of H by T square is equals to H into dou of 1 by T by dou T, but why have you applied constant pressure condition? Because in minus H by T square, you can write that 1 by T, dou of 1 by T by dou T, even if pressure is not constant.
No,
because
no, that is independent of pressure. But since the whole process is going on at constant pressure, you see, we started with constant pressure. The whole process is going at constant pressure.
Yes, sir.
Okay. So because I want to find out how Gibbs energy changes with temperature. So therefore, this is how the Gibbs energy varies with pressure and temperature. So if I want to find out how it varies with temperature, I must keep pressure constant. Then only I will get variation of del G with temperature.
Yes, sir.
Okay. So that is why it is everywhere pressure is constant. So this is independent of whether pressure is constant or not. But since the whole process is at constant pressure, so when you write a partial derivative, you have to write what is condition is kept constant. Clear?
Yes, sir.
Because partial derivative you always have two variables. So when you write partial derivatives, only one is changing, other one is constant. Okay, that's why here there was no derivative, so I did not write anything. But since I'm bringing a partial derivative form, so I'm writing constant pressure. Okay.
Yes, sir.
So this is the one expression I get in. Now you can get similar expression for delta G also. Okay, delta G means Gibbs energy change for a process happening at a particular temperature. Now you change the temperature. What happens to the Gibbs energy change for the process again? Okay. So the change in Gibbs energy at different temperatures for a process. Okay. That is what also is very important. So instead of H, now it will be delta H. Now we are assuming that delta H is independent of temperature. Okay. Delta H is independent of temperature. So therefore, we can write it down in this manner. Or similar, we can write it down in this manner also. These are all identical equations. Okay. So here it is G by T is this. So similarly, I can write it down in terms of delta G by T by del T will be del of C 1 by T by delta T. Instead of H, now it becomes delta H. So that can be written as minus delta H by T square. Assuming that your delta H for the temperature range that which you are measuring or you are carrying out your experiment, in that temperature range, delta H is constant. That is why it has come out of the derivative. Okay. So all these three equations or four equations what I've written, they are collectively known as Gibbs-Helmholtz relations, which basically gives you how Gibbs energy changes when you change the temperature of the system. Okay. Now this is important because what it tells you is that if you know the Gibbs energy change at a particular temperature for a process, then what will be the Gibbs energy change at another temperature? Without performing the experiment, you can actually calculate that part, provided that delta H is constant for those two temperatures. Okay. So that's why it is important in calculating delta G at another temperature if it is known at one temperature. If you know a given temperature, suppose I tell you that at 300 degrees centigrade or 300 Kelvin, this is the a Gibbs energy change. Then you'll be able to find out. And if I say that find out what is delta G at say 50 Kelvin, assuming that delta H is constant and equal to some value. Okay. Then from these expressions, you'll be able to find out what will be the delta G for that different new temperature. Okay. So that is why it is important in finding out temperature variation of Gibbs energy change for any process. Okay. So this is the so-called Gibbs-Helmholtz equations. Now you see in this fundamental equation, Gibbs energy change depends on VdP minus SdT, that means pressure and temperature. In this particular case, we wanted to know constant temperature, how G changes with temperature. So we kept at pressure constant. Now we can use the same expression if you want to know how Gibbs energy changes with pressure. Okay, then we have to keep the temperature constant. Okay, so that also can be found out. That means pressure dependence of Gibbs energy. We can also find out pressure. Here we found out temperature dependence, and for that we kept the pressure constant. Now we can use the similar expression to find out the pressure dependence of Gibbs energy. Then we have to carry out the process isothermally at constant temperature. Okay. So let us see how. So next is pressure dependence. Again, you see dG equal to VdP minus SdT. And as I said, I want to find out the pressure dependence. So I take a derivative of pressure with temperature now kept constant. So therefore, this term disappears. It is actually equal to V, volume. So change in Gibbs energy with pressure at constant temperature is the volume of the system. Okay, it's coming from the fundamental equation. Now, since when you see volume, temperature, pressure involved, that means all are state parameters. So equation of state can be brought in now. Okay, so I can therefore directly use this expression to compute Gibbs energy at a particular pressure given the Gibbs energy value at another pressure. Okay, how simply I can write it down in this manner. So dG equal to VdP, and then if I integrate, if I go from state 1 to state 2, then what is the Gibbs energy at the new state with pressure say P1 to P2? I integrate this, so I get G2 equal to G1 plus this term. Okay, so that means if I know the Gibbs energy at a particular pressure, say P1, I'll be able to know Gibbs energy at a particular another pressure P2 from this expression. Okay. Now this is an doable expression. You can solve it because it involves V and pressure. So you can use equation of state here. Okay, and write V in terms of P, and then you can integrate it out. Now, if you take liquid solid, say as a system contains liquid or a solid, then for liquid solid we know volume is more or less constant. Okay, effect of pressure on volume is kind of negligible, so we can assume or consider V as constant volume. If that is a constant, then simply this integration becomes V into P2 minus P1. Okay, so we write it down like that: G equal to G2 equal to G1 plus V P2 minus P1. So if you know the value of Gibbs energy at a particular pressure, and therefore then you can find out that in another pressure what will be the corresponding G values for liquid and solid, where effect on of pressure on volume is negligible. You can get like this, or often you can, if one of the states is a standard state, then you can write it down like that. Okay, the state 1 is actually a standard state, so you write corresponding standard Gibbs energy, standard pressure, and so on. Now, if you have a gas or a gaseous substance, this V is no more constant because V depends heavily on pressure. Okay, so with slight change in pressure, volume can change significantly. So therefore, now you cannot neglect volume. So what we do is we use now equation of state. We use the equation of state, so convert V in terms of pressure. So we'll get this expression. If we write for ideal gas, PV equal to nRT. So therefore, V equal to nRT by P, and at this isothermal condition, constant temperature. So T comes out, and this is the expression. If you integrate, you get log. So therefore, G will be equal to G0. One of the state is the standard state. If we take, then G equal to G0 plus nRT log P by P0. Okay, this is the expression. Since you know G, similarly you can find out all delta G. What will be the delta G? Delta G will be simply G minus G0 or G minus G2, G2 minus G1. So that will be simply nRT log P2 by P1. Suppose the two pressures are P2 by P1, P2 and P1, then you'll be able to find out the Gibbs energy change. Okay, the Gibbs energy change at two different pressure you will be able to find out. Now pressure is inversely proportional to volume, so therefore it can be also written as ln V1 by V2. Okay, so this is the expression to say how the pressure affects your Gibbs energy of a change, Gibbs energy for a system, and then if you know two different pressures, you can find out what will be the change in Gibbs energy for the process. Okay, so this is basically the temperature and pressure dependence. Now, why this temperature pressure dependence comes? Because if fundamental equations is always our starting point. Remember that fundamental equation is a starting point, and then in this expression it shows that Gibbs energy depends on pressure and temperature. Okay, so that is the for a closed system. We are dealing with closed system. Soon we will talk about open system. Then this equation will be modified. So for a closed system, this is the change in Gibbs energy. Okay, so therefore,
hello, sir.
We can by keeping temperature constant, we can monitor and see how Gibbs energy changes with pressure, or by keeping pressure constant, we can monitor how Gibbs energy changes with temperature. Okay. Yes, quickly.
Sir, how the term VDP came here?
Which one?
Sir, VDP, sir, I didn't understand VDP.
No, this is the
equation.
Equations we derived last class. You were present in the last class?
Yes, sir.
So there actually we talked about this. Okay. So take a look at the last class what we talked, then you will be able to find out. Okay, we derived four fundamental equations, one involving U. This one, today very beginning we talked. This is the du, TdS minus PTV. Then we had EH. This I did not derive it properly, but you can do that. dH equal to TdS plus VDP, and then dG was another expression. So we started from there. Okay, this we derived in the last class. And from here, since it depends on varying pressure and temperature, so that means Gibbs energy will depend on temperature and pressure. So this is the clue why we are looking at temperature dependence on pressure dependence. Now, if I want to find out temperature dependence, then we have to apply the partial derivatives. So only one of them will change, other we have to keep constant. So since temperature dependence, we get pressure constant. And since if we are doing pressure dependence, then we'll keep temperature constant. Clear? And then do the proper derivation. You will get this is basically the working expressions. Okay. Now we are coming to very important role that Gibbs energy plays is to determine whether a change will be spontaneous or not. Okay, what is the fundamental condition? Now, because this change in Gibbs energy actually determines the direction of any transformation. Okay, whether a transformation will be spontaneous or not, or in which direction the process will occur. Okay, if you want to know, then you need to compute the Gibbs energy change for that process. Okay, by looking at the Gibbs energy change, you will be able to conclude whether the process that you are considering is spontaneous or not. Now, how you can get that expressions? Okay. Now, let us start from the first law. This is essentially the first law. Okay, we know that du equal to dq plus dw. Now, u is a state function, so therefore this doesn't matter whether you are carrying out the process in either in a reversible manner or irreversible manner. So I can write it down in like this with the equality sign. So dq reversible and plus dw reversible will be dq irreversible by dw irreversible. Okay. Why I'm doing that? Because spontaneous processes are irreversible process. Okay, so I have to bring in the irreversibility into the expression. Now we already know that reversible work is greater than irreversible work. Now reversible work is greater than irreversible work, following which you need to maintain the equality. And remember, the work is negative here because the system is doing the work. So therefore, to maintain the equality, your dq reversible should also be greater than dq irreversible. Okay, or dq irreversible minus dq reversible less than 0. This is basically nothing but the Clausius inequality. Okay, because what Clausius inequality showed, if you remember, entropy change was dq reversible by t. Okay, and Clausius inequality shows that ds was greater or equal to dq by t. Okay, and it becomes equal to when dq is at reversible process, and it becomes greater than if it is irreversible process. Okay, so in the various ways you can show that the dq reversible, the heat exchange, if you carry out the process in reversible manner, is actually greater than the corresponding irreversible process if you carry out the same change in an irreversible manner. Okay, so this term is less than 0. Now, what is G? Gibbs energy by definition, it is H minus Ts. So I can write it down like this, U plus PV minus Ts. Now, since we are by using this du term, so I take a full derivative of G. So dg becomes du plus PdV, VdP minus TdS minus SdT. All these terms. Okay. Now, what is du plus PdV? That is nothing but the dq. Okay. And then you have VdP minus TdS this term. Now, if you take a constant temperature and pressure, if I take a constant temperature and pressure, then this term SdT disappears and VdP disappears. So what we have, dg becomes equal to dq minus TdS. Okay. So dg becomes
Hello, sir.
dq minus TdS. Okay, there's one line was somewhat missing here. So now, if you try to understand what is dq for any spontaneous process, suppose you take, then for a spontaneous process is dq basically dq irreversible. Okay. Now, when I write TdS, TdS is what? TdS is dq reversible. See, TdS is basically dq reversible. Okay. So that means for a spontaneous change, this dGpt at constant pressure temperature is actually dq irreversible minus dq reversible. Okay. So
Hello,
dq
sir.
irreversible and dq is basically less than 0. Yes.
Sir,
Is it-
PdV is not in the last equation.
Which one?
PdV, sir, PdV.
No, no. Here you see du plus pdv. I have written it as dq. First law. Okay.
Okay, okay, sir.
Okay. From the first law, we have written it like this. Let me tell you once again. Don't get if you have any confusion. We are trying to find out a condition for the spontaneity of a process. Okay, and I told you that Gibbs energy change gives you that information. If you want to know whether a process is spontaneous or not, you need to measure the Gibbs energy change for that process. Now, how we are coming to that expression? This is the fundamental logic behind that. I started from the internal energy expression. The internal energy is a state function. It doesn't depend on how you carry out the process. So this will be equal whether you carry out the process in a reversible manner or in an irreversible manner. Okay, so this is equality. Now we already know for maximum work you need to carry out a process reversible manner. So dq reversible, dw, the work involved for reversible process is greater than irreversible process. Now to maintain the equality, dqr reversible process heat exchange must be greater than irreversible process heat exchange, which doesn't nothing but gives you this expression. dq irreversible minus dq reversible is less than 0. Okay, which actually comes from Clausius inequality. We already discussed in Clausius inequality was this expression, Clausius inequality. ds, you remember, ds was greater or equal to dq by t. I'm not telling what is dq, reversible or irreversible. So if we are writing a inequality sign, now the inequality becomes equality if it is reversibly done. So ds equal to dq r by t. Whereas if the process is carried out irreversibly, then ds is greater than dq irreversible by t. Okay. Now from here, automatically you can know dq irreversible minus dq reversible is actually less than 0. Okay. So it also comes from Clausius inequality. Now this will be needing. That's why I have written like that. We'll need that. Now I come to G, because I told you that Gibbs energy is the function which talks about the spontaneity. So now I write G equal to H minus Ts definition, and then H equal to U plus PV. Again, we know H definition of H is this. Now I take a complete derivative. I write the whole entire differential form. Now du plus PdV is the first law. We can write it on dq. Okay, because we need to bring out this dq expression here. Heat amount of heat exchange happened, plus these 3 remaining quantities.
Excuse
now
me, sir.
put more condition that suppose the process is carried out constant pressure and temperature. So these 2 terms disappears, VdP and SdT. Now I have dg at constant pressure and temperature, change in Gibbs energy equal to dq minus TdS. Now what is dq minus TdS? This TdS means dq reversible. That is clear to you. TdS means dq reversible. Now dq is actually the heat exchange for that process. Now if the process is spontaneous, then this is an irreversible process. So this dq is actually dq irreversible. Okay. So therefore dgpt is becoming what? dq irreversible minus dq reversible. Okay. We already know dq irreversible minus dq reversible less than 0. That means for any spontaneous process, this dg corresponding Gibbs energy change at constant pressure and temperature should be less than 0. Okay.
Excuse me, sir.
Right. For any spontaneous process, therefore delta G for the process change in Gibbs energy at constant pressure and temperature is less than 0. So this is the fundamental most important relationship or condition in thermodynamics. For any process, if you find delta G, if you compute the delta G, and you have to take a look at the sign of the delta G value that you have got. If you see that the sign is less than negative, that means if delta G is less than 0, then the change is spontaneous. If you find that your after calculation the sign is positive, that means greater than 0, then it is not a spontaneous process. So the reverse process will be spontaneous. That will be with delta G negative values. Okay. If you find delta G equal to 0, that means the system is in equilibrium. The system has attained an equilibrium. So it is neither way it is spontaneous. It was spontaneous, but after some time it has come to an equilibrium. Therefore, delta G has become 0. Okay. You have seen these conditions earlier. Okay. That delta G less than 0 is the condition for a spontaneous process. Now here I showed you how you derive. You get that why delta G becomes negative or less than 0 for a spontaneous process. Okay, so we derive that expression.
Sir, I have a doubt, sir.
Yes, where?
Sir, for most of the spontaneous processes, pressure and temperature keep on varying. So how can we conclude that this equation is at different all the instants this relation holds to the delta G is less than 0, or is there some other relation?
No, by definition, whenever you are changing the Gibbs energy for a process, you need to carry out at constant pressure and temperature. Okay, because we are coming from the G is a function of temperature and pressure. See, dG equal to VdP minus SdT. So whenever you look at a spontaneous process, suppose you are performing a chemical process in a laboratory, okay, then you have to carry out the process at a constant pressure and temperature. Say you go to a room, you have a room temperature and the pressure is atmospheric pressure, you perform a process. Then whatever is the, that say A plus B goes to C. So that means that is a spontaneous process under that condition. Whatever you do, there is a pressure and temperature, constant.
Understood.
Excuse me, sir.
Okay. So by definition, has to be done at a constant pressure and temperature. Now, if you change the pressure and temperature, then you will get another kind of delta G value. Now, it may happen for the new under the new condition, new set pressure and temperature, your delta G may convert from negative to positive value. That means that process will not be, spontaneous anymore.
Understood, sir. Thank you.
Okay. Say for example, ice to liquid water, the simplest thing that we understand. Suppose you take a temperature, room temperature. I go there and keep a block of ice. You see ice melts after some time because that 1 atmosphere pressure, room temperature, say 25 degrees centigrade. If you calculate the delta G from ice to water, that will become negative. If you calculate for the reverse, that will become positive. Okay. Same, now you do the reverse. You take a glass of water and put in a deep freezer, minus 20 degrees centigrade. After some time, you will see it is frozen because now you have changed the temperature condition. You might have changed the pressure condition. So now the delta G value changes now. So ice to water is no more spontaneous because delta G will be positive. So water to ice will be spontaneous because delta G will be negative for that pressure temperature. So what I'm trying to say is whenever you are measuring delta G for a process, remember you have to carry out that at a particular pressure and temperature. Okay. All right. So
Yes.
Hello,
this is
sir.
very, very important. This spontaneity, and we always say delta G is less than 0, but always it is delta G at constant pressure and temperature. You should keep that in mind. Okay.
Excuse me, sir. I had doubt in last slide.
Yeah. Where?
Sir, sir here, sir, like the work done in reversible is greater than work done in irreversible, and heat is also same. So if we add the reversible, then won't it be greater than irreversible? So because here equality is also mentioned, and below that.
No. These works are negative work. Okay, system is doing work, so this work is negative.
Okay, sir.
So for negative, you understood now. For negative work,
sir,
to
these
maintain
are
equality. This also should be greater. Clear?
Some is the dW are the magnitudes. dW and for the reversible and irreversible. Sir, because if we add the both inequalities,
No,
then
not
it will become
exactly not magnitude. Say for example, minus 50 and say minus 20. Okay, so if it is minus 50 and suppose this is minus 20, okay, then to maintain the equality, this has to be greater than dq IR.
Yes, sir.
Okay, that's why. So it is with respect to sign I am talking about when I say greater or less.
Yes, sir.
So minus 50 joule is a greater work than minus 20 joule in thermodynamics. Okay?
Yes, sir.
Okay. Now we are going to see an important experiment and its application in practical applications like in cooling of gas. Normally we see that if a gas is expands, okay, expansion means it is actually from high pressure to low pressure. If you reduce the pressure, then a gas expands. Most of the time you see that normal regular gas, this expansion is associated with temperature drop. Okay, so that is known as the cooling of a gas. So Joule and Thomson performed an experiment and tried to explain this cooling process. Okay, and we'll see how using thermodynamics you can show that. Now, what is Joule-Thomson effect? It is basically a simple experiment. What you have a kind of a chamber like this, which is separated, basically a cylinder fitted with piston on two sides, and there is a kind of a membrane or a kind of a porous separation between the two, through which gas can pass from one side of the chamber to the another side. And on the left hand side, your pressure is high, and you have a certain amount of gas at a particular temperature, a particular volume. Okay, you have taken it. So a fixed amount of gas with a particular volume V1 and temperature. Now this gas is passing from the left hand side to right hand side. Okay, how? By the movement of these two pistons. So slowly this piston is pushed in this direction and this one is pulled in this direction. Okay, and why this expansion will happen? Because always pressure is P2 kept below P1. Okay, therefore it's going from high pressure to low pressure. So there is pressure P2 is low, and this right hand side, suppose the temperature and volume is V2 and T2. So you know that V2 must be greater than V1. Okay, and our observation shows that T2 is lower than T1. Okay. We will show why this temperature becomes low on expansion. And this whole system is kept insulated from the rest of the universe. That means you can see this entire system is insulated. That means all the exchanges that are happening under adiabatic condition. No heat exchange. Okay, clear? Now what happens is that this entire process, this entire amount of gas is passed from left hand side to right hand side. Okay, and then you stop the process actually. So gradually these pistons is moved in two directions, so that entire gas comes out from left hand side to the right hand side. Now due to this process, what is the work done on the left hand side? You remember always we are keeping the pressure constant. So this is a compression at constant pressure, and this is an expansion at constant pressure also, P2. So P1 is constant, so therefore it will be pressure into volume change. That is the work done. So what is the volume change? Volume change is initial volume is V1 and final volume is 0. So basically the work done is actually your P1 into V1. Okay, it's a compression work. Now the work done by the gas. This was work done on the gas because this is compression and this is expansion. The gas is doing the work. So what is the work done now? Again, pressure is remaining constant throughout P2, and volume initially was 0, left hand side, and then it has attained a volume of V2. Okay, so this is expansion work. So work done by the gas is, we know, the negative, so it is minus P2 V2. Okay, so this is the work done on both sides. Okay, left hand side on the system and the right hand side. So what is the net work then? Net work during this entire process of transferring the gas from left hand side to right hand side. What is the net work done? Net work done will be simply sum of these two. So P1 V1 minus P2 V2. Okay. Now this is the work done. Now what is delta U? And internal energy change. Internal energy change delta U is simply U2 minus U1. So that will be equal to U2 minus U1 will be simply because you know Q is 0, adiabatic process. So therefore entire work done will be reflected in the internal energy change. Okay. So delta U is simply equal to W. Therefore delta U equal to P1 V1 minus P2 V2. Okay. This line is not very clear, but what I did here is that simply I have taken U1. This means what? U1 plus P1 V1 equal to U2 plus P2 V2. Okay. If I take U1 on this side, then U1 plus P1 V1, and I'm taking P2 V2 on this side, so U2 plus P2 V2. Clear? So what is U1 plus P1 V1 means? U plus PV. U plus PV is basically the enthalpy. Okay. So are you following? So this side is basically U1 plus P1 V1 and U2 plus P2 V2. That means this is enthalpy. Here I've written H1. If you can see H1 equal to H2. Okay. So the enthalpy on the left hand side is same as the enthalpy on the right hand side. So that means there is delta H is equal to 0. This entire process, there is no change in enthalpy. Okay. So this process is therefore what we call is isenthalpic expansion. Isenthalpic expansion, because an expansion where enthalpy remains constant. Okay, you learned about isothermal, adiabatic. This is isenthalpic expansion because enthalpy change remains 0. There is no enthalpy change. Okay, or in other words, enthalpy remains constant. We showed that in this manner. So the work done on both sides, and since adiabatic process, so this work done, net work done is same as the internal energy change, delta U. And then now if you look at this, write down this expression from here, you know, U1 plus P1 V1, which is basically H of 1, you know, your enthalpy, and U2 plus P2 V2, which is the H2. Okay. So that means for the entire process, enthalpy remains constant. Okay. Isenthalpic process.
Excuse me, sir.
Yeah.
So are we considering initial volume of gases are 0?
This side, right hand side, initial volume was 0. Yeah.
And left hand side?
Left hand side initial volume was V1, and when entire gas is you know transferred, it becomes 0 final volume. So initial volume V1, final volume V0, 0. Here initial volume 0, final volume V2.
That's why you have written work done in left is P1 V1.
Exactly, yeah.
Okay, sir.
So it is finally 0 minus V1 volume. Here the volume change is V2 minus 0. Oh, sorry, it is from, yes, V2 minus 0, final minus initial. Okay, that is why the work done. So from here we showed that there is no enthalpy change during this entire process. Now, what we see in general effect of this is there is a decrease in temperature. So the temperature drop on the right hand side. This is known as the Joule-Thomson has showed. This is known as Joule-Thomson cooling, or the effect of pressure on temperature basically. Now, not necessarily that always you will get a cooling. That depends on certain conditions, but under normal conditions, room temperature and all, most of the gases, they show that drop in temperature. So therefore, often it is just called a cooling. We will show you it can be heating effect also, cooling effect also, depending on the conditions. So in general, this is known as Joule-Thomson effect. Okay, what is the effect? Effect means this is the effect of pressure on temperature. Okay, you have changed pressure from left hand side. You had a one pressure P1, right hand side you have another pressure. Okay, so this is the effect of change of pressure on temperature of the gas. Okay, effect of change of pressure on temperature of the gas. How to quantify that? For that, one parameter was suggested. Parameter was defined. That is called Joule-Thomson coefficient. That is the rate of change of temperature with pressure. Okay, del T del P under constant enthalpy, because we showed that entire process enthalpy remains constant. So that's why this term was defined, one coefficient parameter. So looking at this value, you can tell whether this effect will be cooling effect or heating effect. Clear? How? So if you take a look at that, you know, P2 is always less than P1. Here we told you left hand side is high pressure, right hand side is low pressure. So P2 is always less than P1. So dP is always negative. Change in pressure is always negative. Okay. Now dP is negative, then if delta T is also negative, then only mu becomes positive. So two possibilities. dP is always negative. Now there is a two possibility. dt can become either positive or negative. Okay. Now if dt is negative, then mu jt becomes positive. Or if dt is positive, then dP is negative, so therefore mu will become negative. Okay. So looking at the sign of the mu, this coefficient, you can tell whether there will be heating effect or cooling effect. So if dt is also mu is to be mu positive, dt must be negative. So that means temperature will drop. Final temperature will be less than the initial temperature. So there is a drop in temperature. So that is a cooling effect. Now, if we find that mu jt is negative, then automatically means dt was positive. Okay. So dt positive means there will be temperature increase. So that means that was a heating effect. Okay. So that's why the Joule-Thomson coefficient is an important parameter. If you calculate that, and by looking at the value, you will be able to say whether under that condition you will see the gas is being heated up or it is being cooled down. Clear? So that is what is known as the Joule-Thomson coefficient. Now the most common thing what was observed is that except for gases with a very low mass, for example very light molecules like hydrogen and helium, most of the gases actually cool down under normal conditions. Okay. Now this doesn't mean that hydrogen and helium behave differently. They also show the same behavior, but that is shown at a very, very low temperature, not under room temperature. Okay, that is why initially it was thought that hydrogen and helium are behaving differently, but it is not like that. They also exactly show the same behavior. Only the thing is that their temperature pressure range is different than most of the other real gases. Okay. So they cool down at a much lower temperature. Okay. Now, so what we need? We will try to now generate an expression of this mu, the Joule-Thomson coefficient, and try to connect it to some equation of state so that we can calculate these values. If we can write it down in terms of pressure, temperature, volumes, and so on, then we'll be able to compute it easily with the help of the equation of state. Okay. So let us try to do that. And some measurable quantities, actually, we will try to convert this. So since we are dealing with, say, age is a constant here, we want to try to change this age with something else. So therefore, let us write age, the Helmholtz, your enthalpy. So how enthalpy, we can write it down as a function of pressure and temperature. Okay, because we are dealing with temperature pressure change. So let us write that. Enthalpy. So the corresponding, if I take a differentiation, we write like that. Okay. So dH equal to del H del P T dP plus del H del P dt. You know this expression. Now from this experiment, we have already shown that dH equal to 0. It was isenthalpic process. There is no change in enthalpy. Okay. If dH equal to 0, so therefore from here you can write it down like this. So del H del P at constant T, constant pressure dt equal to minus this one. This way we have taken the left hand side. Why? Because I need to get this expression del T del P. Okay. So this is like that. Now I take this one. So dt dp I take on this side, del T del P at constant H. Then it becomes this term minus del H del P at constant T, and this one comes in the denominator, del H del T at constant P. Okay. I hope this part is clear to you. The simple kind of algebra. So I do that. Now, see del T del P at constant H, which is nothing but mu. I found out that expression left hand side. Right hand side, what I find? Del H del T at constant P, this is nothing but Cp. Heat capacity at constant pressure. You know that Cp equal to del H del T at constant P. We discussed that earlier. Okay, Cp equal to heat exchange dQp at dt. Now dQp is equal to dH, you know that. So therefore, this term is the heat capacity at constant pressure. So I have minus 1 by Cp into del H del P at constant T. Okay, so this is an expression of mu. Now in terms of enthalpy, pressure, temperature, we have found out. Now again, if we take an ideal gas, we know del H del P, we have already proven it and applied it also several times. This term is 0. Okay, so that automatically means mu Jt equal to 0. So Joule-Thomson coefficient 0 means you have neither heating nor cooling effect. Okay, so that's why Joule initially, you remember we talked about Joule experiment, because he could not differentiate between ideal real gas. He always said that there is no effect. Okay, but we know only for that is valid only for ideal gas, because this for only ideal gas this term is 0. Okay, so if you have ideal gas, there will be no effect on heating or cooling. If I ask you why, this is very obvious reasons, because the gas is ideal. Okay, now what we are doing, we are basically expanding the system. We are changing the volume. Volume is higher, V2 is greater than V1. We are basically changing the volume. Now, if you change the volume, what happened to the molecules or the material present? Okay, if you expand the volume, the intermolecular distance simply increases. Okay, so distance between the particles increases because you have a more volume now. If you take a small cylinder of a gas and then if you expand in the room, it finds a larger volume. So therefore, only thing is that it spreads out. We know that means that distance between the constituent atoms or molecules when it was in a tight cylinder was much less, and now it is much more. So distance increases between the particles, but it doesn't affect because ideal gas do not interact. So whether particles are very close or particles are very far away from each other, it doesn't affect them. Okay, so therefore there is nothing happens to the gas if it expands. Okay, for ideal gas, but for real gas, we know this is not equal to 0. For real gas, this term is not 0. So therefore, mu also is not 0. So mu will have a non-zero value now. Okay, and it will have a non-zero value. So two possibilities, one is positive and negative, what we discussed. So depending on that, you can see either there is a cooling effect or there can be a heating effect. Okay, so I hope this part you understood. Now we will try to further simplify it and see whether we can connect an equation of state with that. Okay, that is our next goal. Okay, so far here we proved, we actually defined this Joule-Thomson coefficient, and we showed that for ideal gas it will be there is no effect, but real gas there is some effect. Now we want to see it contains enthalpy. We want to convert it into state variable. That means pressure, temperature we have. If we can make it pressure, temperature, volume, the entire expression of mu, then we can actually calculate from equation of state. So how we are going to do? See, again, you see that we take help of these fundamental equations. Again, another example where you need to use that. And Maxwell relations will use. So dH equal to TdS plus VdP, we know. Okay, because what we need now, we need to convert this del H del P at constant temperature to some measurable things. That means in terms of pressure, temperature, volume. Okay, so immediately your clue will be that I have to start from fundamental equations and then apply Maxwell. Okay, Maxwell gives you a bridge to convert to pressure, temperature, volume, those state parameters. Okay, so since we are dealing with delta H, so corresponding fundamental equation you have to use. So therefore DH you have to use. DH equal to TdS plus VdP. Now what we need to replace this term del H del P at constant temperature. So therefore I do that derivative. I take a derivative of this one with respect to pressure at constant temperature. So if I do that, then this term is this T del S del P at constant T, and this term becomes volume V. Now we have a term came here, entropy. Normally entropy is a dangerous term. We always want to avoid this one because it's very difficult to measure entropy. So Maxwell equation helps us. Remember the rectangle we discussed? If you do that, SPT will give you VTP minus sign will come because you ended up on the vertical line. Okay. So del S del P at constant T, we can convert to minus del V del T at constant T. Now you see very nicely we get volume, temperature, pressure, state parameters. Okay, so I write it down here. So del H del P at constant temperature is basically this minus T del V del T at constant temperature volume plus volume. See, all these things are connected with state parameters. So therefore, we can use equation of state. So now mu Jt becomes, mu Jt was minus 1 by Cp this term. So this term we are replacing it with this. So it becomes 1 by Cp this term T del V del T at constant P minus P. Okay, now this is very useful because if you see a right hand term, right hand side, what you have written is volume, temperature, pressure, which are connected to equation of state. So therefore, if we know the equation of state, then from there we can actually get the expression of Joule-Thomson coefficient. Okay. So if you know the equation of state, from there we can find out these derivatives and we can find out what is mu Jt expression for that particular type of gas. Simple equation, say take ideal gas. Ideal gas, if you again take PV equal to RT, if you find the derivative will be equal to V. So therefore again V minus V, mu Jt will be 0. Nothing new, we already know that for ideal gas mu Jt is equal to 0, but we have from this equation of state expression also we can prove that. Okay. Now suppose you take a Van der Waals gas, okay, which is an example of a real gas, one of the real gas equation of states. Now Van der Waals equation you all know, P plus A by V square into V minus B equal to RT, where you have a pressure correction and volume correction terms. So if you use that, and from there you can find out these derivatives del V del T and multiply all these things. If you compute, you will get, you can do that yourself, small derivatives, and you will get this expression. For any real gas, following Van der Waals equation, this is the expression of Joule-Thomson coefficient. Okay, this is the expression of Joule-Thomson coefficient. Now what you see from this expression that, so what are the things on which mu therefore depend? So therefore it depends on the nature of the gas also. See, the expression contains A and B. A and B are what? A and B are two correction terms in Van der Waals equation. One is the pressure correction, one is the volume correction term. And this depends on the nature of the gas. So A and B will be, say, carbon dioxide will have a particular value. If you take nitrogen, will have a particular different values. So this depends on therefore nature or the identity of the gas. So therefore mu, Joule-Thomson coefficient, which is a measure of heating or cooling effect of the gas on expansion, depends on not only identity of the gas, nature of the gas. It also depends on the temperature, pressure, etc., and the intermolecular interactions also. Okay. So this is expressions that one can derive. There is no need to remember. You can always kind of mu Jt expression. This expression you have to remember what is Joule-Thomson coefficient. Okay, and other things you can very easily work out. Now I will come back to this graph little bit later. So this is therefore from this expression it is obvious that it depends on the even the nature of the gas also, which gas you are talking about. Now see, there are two expressions here. So that these two values, say one is 2A by RT, another was B. So therefore this relative comparison of these two, one is this ratio 2A by RT and B, that will tell you whether mu Jt will be positive or negative. Clear? So if this term is greater than B, then mu will be positive. That means cooling effect. If this term is less than B, then mu will be negative. So that will be a heating effect. Okay. So most cases what we find at low temperature means room temperature and below. If you take a low temperature, then this becomes very small. So therefore this ratio becomes large. and that becomes greater than B. So this term becomes greater than B. So this term greater than B means this term is positive, so therefore mu becomes positive, so that is a cooling effect. Okay, so that happens at low temperature. Now if you increase the temperature to high, very high temperature suppose, then say thousands of degrees or so, then what happens? This term becomes very small now because T is in the denominator. So now this term can become very small and smaller than B, the volume correction term of Van der Waals equation. Then what will happen? Mu will become, overall it will become negative. So mu becomes negative means you will have a heating effect now. Clear? So the comparison between the two, at different temperature these values will change. Now you can see that if you systematically change temperature, say from low temperature to high temperature, you will see cooling effect transferring to heating effect. Same gas, same nature of gas, A and B are same, but the temperatures are, if you keep on changing, then at some point of time, you know, this term will become, instead of greater, it will become less at a high temperature. So cooling effect can become a heating effect at a different temperatures. That means there must be a temperature where this cooling and heating, there is an inversion is happening. Cooling becomes heating suddenly. So there must be a point of a temperature where there will be no effect. Mu J2 will become 0 because mu J2 positive when there is a cooling effect. Then mu J2 decreases as temperature increases. So it becomes positive value will come down and it will become 0 and then it becomes negative. Okay. So when mu J2 becomes 0, that is the temperature we call, that is an inversion temperature. Okay, so what is inversion temperature? This you should note down. Inversion temperature is the temperature where there is neither heating nor cooling. And at that point, therefore, mu J2 should be equal to 0. It will behave like an ideal gas at that point of, okay, at that particular temperature and pressure. So at a particular temperature, when mu J2 becomes 0, neither heating or cooling. Okay. And then you can actually find out that expression. So in mu J2 equal to 0, that means actually this term will be 0, 2A by RT minus B. Okay. So you can put it this value to 0. From there you can find out what will be the inversion temperature. So 2A by RTI minus B equal to 0. If you put, you find out the inversion temperature. So see, inversion temperature is a constant value for a particular gas because it depends on A and B. Okay. A and B are the characteristic of the gas and are constant. So therefore, this TI inversion temperature is a fixed temperature for a particular gas. Say carbon dioxide, TI is some value. If you go to the nitrogen dioxide, it will have another value. Okay, because A and B values will be different. So every gas is characterized by a particular temperature, the inversion temperature at which you will neither see heating nor cooling effect. Okay. Now for hydrogen and helium, what happens? For a very, you know, hydrogen heliums are very small sized particles. Now for hydrogen and helium, the size is very small. This A term is very small. This one, A is very small even at a normal temperature. So if A is very small normal temperature, so even at a normal temperature, B is greater than this ratio. That means mu becomes negative. Even at low temperature, B is greater than 2A by RT. So therefore mu becomes negative. B is greater than 2A by RT, so mu is negative. Okay. But if you go to very low temperature, A is small, but if you make T is very small, then again at some point of time this ratio may become greater than B. So you will again see cooling effect. But this cooling effect of these gases will occur at a much lower temperature than that observed for other gases, okay, in nature. So at a very low temperature, so same behavior is shown by hydrogen helium. It is not that they are exception, but only thing is that the temperature range or the temperature point, inversion temperature at which heating and cooling effect, interconversion happens, that temperature is much lower than all the other normal, regular gases. So that's why normal temperature, hydrogen helium, they get heated up if you expand them instead of cooling. Okay. So I hope this part you understood why we derived, and this is why you can see a heating effect, and then after some time you see a cooling effect. Okay. So this is the findings. Now here I try to show you, try to give you the explanation why this heating effect and becomes a cooling effect and so on. Okay. Now here I am showing you some a figure with several lines. So what it shows, what this graph shows actually. Now this graph shows, let us come back here, this picture. What I have done is that, suppose you take a series of P1, T1, different values of P1 and different values of T1. This is something that you can define on the left hand side. So we arbitrarily choose some P1 and V1 values. And then depending on the P1, you can choose a series of P2 values. Only condition P2 has to be less than P1. Okay. Suppose P1 you decide 100. Then P2 has to be, can be any value less than 100. Okay. So you decide value as 90. Then you carry out the entire expansion process, measure the temperature. Next, P1 you keep the same 100 atmosphere, P2 you make it say 80. Again, you carry out the process, you will get another temperature, you will get a T2. Okay, like that. So you take an arbitrary set of P1, T1 value, and then various values of P2 you keep, and every time you measure T. Okay, so the final temperature this side T2. And then we plot that. If we plot that, we get this type of curve. So what I am plotting is here actually T2 by P2, right hand side pressure, right hand side gases temperature. Okay, so I will get something like these curves, some lines or curves. So each one of this line, each one of this line corresponds to one particular value of P1, pressure and temperature. Okay. So this line corresponds to one particular P1. This line corresponds to another particular P1. Now I change the P1 value. If I change the P1 value, I told you I kept say 100 atmosphere. Now suppose I make P1 at 200 atmosphere. Okay. Again I keep 200 fixed and I keep on changing different P2 values less than 200. Okay, and measure the T2. So I will get another set of P2 versus T2. That may be another line. Clear? So each one of these lines corresponds to one particular value of P1 and T1. Okay. And these are actually the plot of P2 and T2, right hand side, what we are observing. So you will get a series of this type of curve. Okay. I hope it is clear how this graph is drawn. Okay. Assume that you are doing that experiment, you collected the data and you are plotting. Okay. Now each one of these we call isenthalps because we have shown that this line enthalpy remains constant. So these are called isenthalps. You know, isotherms, isobar, like that. So these are called isenthalps, these lines, because along this line enthalpy remains constant from the Joule-Thomson experiment. So these are simply the isenthalps. Now, what is the Joule-Thomson coefficient? Joule-Thomson coefficient is simply the slope of this curve. So the slope of these lines will give you the Joule-Thomson coefficient mu values. Okay. Now, if you see at a very, very high temperature and all, you will see that what is the slope? This slope is always negative. Okay. Similarly, at a very low temperature, you will see that slope is always negative. So slope is always negative means what? Slope negative means your heating effect. So if the slope is negative, then if you reduce the pressure, what happens? You are going right to left. If you reduce the pressure, temperature increases. You can see that, right? If the slope is negative, so you reduce pressure, temperature increases. So that is the heating effect. Okay. Now suppose if you reduce the temperature, then at some point of time you will see that the lines have a positive slope. So positive slope means if you reduce pressure, temperature drops. Okay, so you will have a cooling effect. Okay, and so set some in between curve. Suppose in between very high temperature, low temperature. Suppose it's a normal room temperature kind of a curve. Most of the gases, the situation happens like that. Suppose you are at a kind of high pressure. Now mu jet slope of the curve is negative here. Now if you reduce the pressure, temperature increases, so there is a heating effect. It happens, and if you come to that particular point where you will see that the slope will be 0, that means mu jet is 0, and after that you see slope becomes positive. So here drop in pressure drops the temperature. So this line shows how an heating effect after crossing the inversion temperature becomes a cooling effect, shows cooling effect now. So this point is the inversion temperature. If you connect these inversion temperatures, you will get this is a kind of a what we call inversion curve. So below this point, below this within this region, you will see cooling effect. Okay, and beyond this, you will see that there is a heating effect. Okay, so generally you see there are two inversion temperature at either at a very high temperature and a very low temperature. And as I told you, temperature is above the upper inversion temperature, then there is a heating effect. And when it drops below the upper inversion temperature, there is a cooling effect. Okay, and this inversion curve actually connects all those points where the slope is 0. Slope of the curves are 0. Okay, so it runs through all the points of the isenthalps that we have shown here. When slope becomes negative to positive, that means at that point slope is 0. Okay, so this is what is happening. Slope 0 means at inversion temperature I have written mu jet equal to 0. That means the gas is showing an ideal behavior. Okay, now this cooling or heating effect that he talked about. Now what is the explanation? Okay, why this at some point of time, at given pressure, you see that there is a cooling effect, and a particular pressure temperature, you are seeing a heating effect. How to explain this? Okay, now this will depend on several factors. One is of course identity and temperature pressure. Okay, it is also important that what type of interactions. So the intermolecular interactions actually play an important role here. Okay, what does this role play? Say, this is a curve which in general shows how a pair of interaction happens between two particles. Okay, I hope you have seen this curve sometimes. This means that suppose along this line, one particle is, I fixed it here in the origin. Then another particle, means another atoms or molecule, it is coming to approaching this particular particle along this straight line. From infinity, large distance is coming close. What we see, when the particles come closer, any two bodies in this universe, they attract with each other, we know. So therefore, even if they're very large distance apart, there will be either a very small, or although it is insignificant, but a very small negative interaction energy between them, potential energy. Okay. Now, when they come closer, this particle, you see they feel attraction. So the potential energy actually drops. Okay, there is an attraction now, dominates. Now this potential energy drops and it reaches a minimum where this is the most favorable position where the second particle would like to come and stay. Okay, so this is the most stable configuration between particle number 1, particle number 2. Now, if I try to bring this particle further closer to particle 1, then repulsion starts coming into the picture. See, always there is attraction and repulsion. Now the question is which one is more, which one is dominating. So when the particles are far away from each other, then generally attraction dominates, because repulsion is even much shorter range compared to the attraction. Okay, unless the particle comes very close to each other, there is no repulsion. Or repulsion effect is very small, attraction dominates. Now when I try to bring closer, you see that energy now starts increasing. So that means the repulsion has come in now into the picture. but still the energy is negative. That means still the particle can approach little bit. But after some time, you see the repulsion becomes very, very dominant and energy becomes very high. So that means this particle cannot approach further. This we call a repulsive wall. That is a large wall and it goes to infinity. Okay, so the particle cannot approach them. Here repulsion is so dominating, it plays the important role, or it determines the characteristic of the gas. Okay. Now the question is, which one is the dominating factor in this case? That will determine your either heating effect or the cooling effect, like that. Now suppose that attraction part, interaction is more important. See, this part is important for the particles. Okay. That means most of the particles are within this type of distance from each other. Now if this happens, then what I'm doing now in the Joule-Thomson experiment, I'm expanding the system. Okay, because volume is increasing. So basically this is an expansion. Now if I am expanding the volume, then what happens? Then the distance between the particle increases. Okay, distance between the molecules, atoms, particles, they increase because I'm in this attraction region. Okay. Now if I increase in the distance, what happens therefore? See, potential energy increases. Okay. Most favorable distance. Now I have expanded the system, more volume available. So interparticle separation increases. So that means potential energy C keeps increasing. Okay. It may be negative, but say it was minus 50, now it has become minus 30. Okay. That means potential energy increased. Okay. Now if the potential energy now increases, then remember the entire process or the system was isolated. If you remember, this entire process was isolated. So there was no exchange of isolated system, no exchange of energy. Okay. So therefore total energy must be conserved. So for total energy conservation, if potential energy increases, kinetic energy has to decrease. Okay. The kinetic energy will decrease. Now if the kinetic energy decreases, then temperature has to decrease. So the gas will cool down. There will be decrease in kinetic energy of the gas. And you know equipartition theorem, kinetic energy is connected to the temperature, is proportional to the temperature. Okay. So therefore kinetic energy decreases, so temperature also drops. So you see a cooling effect when the attractive interaction is dominating between the particles. Okay. Now you see, suppose where repulsive interaction is very dominating. For example, when there is a very high pressure, particles are squeezed to come very close. Okay, high pressure. Then you will see this repulsive force is very dominating. Okay. Now if the repulsion force is dominating, then what happens? You are expanding the system, so volume increases. So when your volume increases, particle separation increases. So particle will become happier now. Okay, they have more space. So what will happen? You see there will be a decrease in potential energy. So potential energy will decrease for the particles because distances are more now. So there will be a drop in potential energy. So if there is a drop in potential energy, again for total energy to remain conserved, the kinetic energy should increase. So the particles' kinetic energy will increase now. So because kinetic energy increases, so that temperature will also increase. So you will see a heating effect. So when there is a repulsive interaction, if that dominates, then you will see a heating effect. And when the attractive interaction dominates, you will see a cooling effect. Okay. So therefore, cooling and heating depends on, is very important, how the particles interact. What is the strength of interaction and which interaction is playing important role. Okay. So this is essentially a molecular kind of mechanism to explain this finding of Joule-Thomson effect. Okay.
Sir, I have a doubt in the second graph.
Yeah, I will come back to it. Okay. I will come back to it. Okay. What I will do. Okay, you tell now anybody has any doubt, because we have covered, see whether Joule-Thomson, this experiment and all you understood. Okay, then I will, before I go to the next. Yes, any doubt?
Sir, the potential energy versus distance graph, is it does it depend on temperature as well? Means
Yes.
For different temperatures, the graph will vary. Is that right?
Yes, but the graph nature will remain the same. Okay,
Okay, sir.
graph nature will remain the same.
Yes, sir.
This will remain the nature the same. Only thing is that if you increase the temperature, then what will happen? You will have a potential energy kinetic energy conversions rate will change. Because if you increase the temperature, particle kinetic energy will increase, so there will be more and more collisions between the particles. Okay, so there will be increasing number of collisions. Now, when you have a increasing collision, then what happens? Increasing number of collision means during the collision, your kinetic energy temporarily transferred to potential energy. Okay, so your potential energy may tend to increase. Okay, and if your system is completely isolated, accordingly your kinetic energy will either increase or decrease. Those things will happen. But this is a general picture of how a particle interaction between two particles depends on your separation between them. Okay. So the nature will remain the same. Only thing, your kinetic energy, potential energy, that part there will be a readjustment between them. If you keep the entire system isolated, there is no heat exchange. Okay, if kinetic energy increases, potential energy has to decrease. If potential energy decreases, kinetic energy has to increase. That thing will happen. But potential energy nature will remain the same. Because potential energy actually depends only on the separation between them. So you understood? So potential energy exclusively does not contain any temperature term.
Yes, sir.
Okay, it comes indirectly. Potential energy only depends on the separation between the particles, distance between them. Now, if you make the distance more, then of course potential energy increases. But if you make the distance less, potential energy can decrease. So that is the thing. But so it is basically independent of temperature explicitly. Okay, temperature has direct influence on the kinetic energy.
Yes,
okay,
sir.
Understood?
Yes, sir.
So anybody, if you have any doubt on this part, you can clarify. Okay, so I hope that there is no doubt. So I will quickly just enter into the next part and then probably continue in the next class, because our time is limited this time. So, but before I go to the next one, because we have basically completed the discussion on the closed systems. Now I will bring in the open system into our discussion. Open system means where the number of particles changes, exchange of particle between system surrounding across the system. So we'll bring in that how thermodynamic equations are modified if the system is open. Okay, so that we'll start enter into that open discussing on the open system. So far we discussed everything with respect to the closed system. Okay. So let me quickly see if you have any doubt on this. This is, we started with this basically use of different fundamental equations and Maxwell relations. Okay, if we do like this, then also those equations you will be you'll be more comfortable with using those equations. So first we started one fundamental equations and we tried to derive this so-called thermodynamic equation of state. Okay, why it is called thermodynamic equation of state? Because it's a thermodynamic parameter U, and this is basically it's a pressure. This pressure comes for the interaction between the particle. Again, as we discussed, if you change the if you change volume, then what happens basically? Basically, again, particle separation changes. Okay, if you change the volume, because this change says internal energy with respect to volume. So if you change the volume of the system, potential energy changes. Okay, because the distance between them changes. So if the potential energy changes, then internal energy also changes. Okay, so that's why it is called internal pressure, and it comes from intermolecular interactions. So this is known as the thermodynamic equation of states, and you can have an equivalent expression with respect to enthalpy also. Then this was most important, this Gibbs energy variation with temperature and pressure, because most of the time you will, we carry out processes either at constant temperature or constant pressure. So what happens to the change in Gibbs energy? That will be very common that we calculate, because change in Gibbs energy is again connected with the spontaneity. So this is an important part. So we try to derive this expression, which can be used to find out how Gibbs energy changes with temperature. Okay, these are different set of equations known as Gibbs-Helmholtz equation collectively. And in deriving this expression, we have assumed one thing, that is this enthalpy is constant. Enthalpy does not change within the temperature range that you are talking about. Okay. So then, to do the temperature dependence, this is the fundamental equation from where we started. So to do the temperature dependence, we took a derivative of T. Now to do a temperature dependence of pressure dependence, we will take a derivative with respect to P. That is what exactly we did it here. And then we got volume. So volume means it's directly we are getting something from the state variable. So therefore we can simply integrate these and we can see that liquid and gas, we get a working formula. So numbers can be given, you will be able to compute delta G values. Then this is important to delta G. We know that delta G is connected to spontaneity. We also studied that delta G is less than 0 means it's a spontaneous process. It's a favorable process. So how it becomes delta G less than 0, that we try to show. Okay, we obtain that expression. And these are three possibilities: delta G less than 0, greater than 0, equal to 0, and depending on the values, whether it's spontaneous or non-spontaneous, whether or it is in equilibrium, like that. Okay. Then this application of this we took up. This is the Joule-Thomson expression. I hope you understood. I explained already several times. This is basically passage of gas from high pressure to low pressure, and in general there is a change in temperature. So, and then we showed that this is isenthalpic process. This parameter is the kind of scale. This scale tells you whether there will be effect, will be cooling effect or heating effect, looking at the value Joule-Thomson coefficients. And the Joule-Thomson coefficient can we can bring in actually the equation of state parameters, again using the help of fundamental equations, Maxwell. Okay. And then finally, I showed you that because this is a fundamental general equation in terms of equation with volume, temperature, pressure, so you can bring in the equation of state. Two example I took: ideal gas, this will be 0, we already know, and say Van der Waals gas, you will have some expression. Okay. Now there are two terms here, two competing terms, 2A by RT and B, depending on which is greater than what, which other one. You will have mu Jt either positive or negative, and this is the result. We see either cooling effect or heating effect. So at some pressure, cooling effect can turn into heating effect or vice versa. That means there is a transition. There is an inversion from heating to cooling effect. At that point, mu will become 0. So from there, you can get an important expressions. Okay. So if A, B values are given, suppose Van der Waals gas follows Van der Waals equation, then you can very easily find out what is the value of T. This is a fixed value, a constant for one particular gas, independent of temperature or anything. Okay. It only depends on the nature of the gas. And then we try to give you a molecular explanation why this is happening. Okay. So which of the two interactions dominate? Okay. Remember, this is valid if you have performed the experiment in an isolated manner. Okay. There is no heat exchange with the surrounding. Okay. So if you have understood this part, I will just let me introduce this little bit. Then we'll come back next class. What is open system? All discussion so far was related to closed system. No exchange of particles. Particles was constant, so we did not even bring that into the discussion. Okay. Now we are having an open system. That means that the exchange of matter is happening now. Okay. So there is an exchange of matter from one system to between systems or system to surrounding. Okay. So the composition can vary now. Okay. How will you handle that? So that means now the number of molecules or the composition, that is also a variable. Okay, coming into the all thermodynamic equations. Now you have to modify. So now for simplicity, let us assume that we have a homogeneous systems. Like we have a system on homogeneous system and different components are present. A liquid mixture, for example, all are in one phase. So it is easy to understand. Okay. Suppose you have a say water you have taken and you have added several salts, different type of salts into it, soluble, and then they are soluble, so it becomes a homogeneous solution. Okay. How will you write down the Gibbs energy now? Okay. And then subsequently change in Gibbs energy if you are carrying out any process. So G, is an extensive property. It depends on the matter. So far we wrote a function of pressure and temperature because all the number was kept constant. So we did not bring in, but now numbers can vary. Okay, composition can vary. So that means it will be also a function of all the different constituents that are present and their composition. Suppose N1 mole of one component, N2 mole of second component, and so on. So G will be a function of all now. Okay. So what will be the change if I differential form? If I take a derivative, dg will be simply partial derivatives we take with one respect to one, say pressure, then all temperature and all the compositions are constant. Similarly, the second term is this with respect to temperature, pressure, and all compositions are constant. So this term essentially represents a closed system, first two terms, and this much we discussed so far. Okay. So VdP minus SdT. This is basically VdP minus SdT. Okay. So this is constant composition. Now you have the additional term coming from this, where how Gibbs energy changes when one of the composition changes, keeping the pressure, temperature, and composition of all the other constituents fixed. That is represented by this term. And you have n number of terms, so this goes over I equal to 1 to n. Clear? So this is the total change in Gibbs energy for open. So this was closed system, and this is now modified or extended by these terms to consider the system being open. Okay. Now this term del G del N, we call it chemical potential. This term comes into the picture now. Term is important for open system. We call it chemical potential of the ith species. So it's called mu I, then dni, sum over all the species. Okay. Now, so what is this actually physically represents? If you consider the process at constant pressure, temperature, then these two terms disappears. Okay. Now remember DGPT, when we were deciding a couple of classes back, we studied when we talked about Gibbs energy and Helmholtz energy. We talked about that Helmholtz energy change was represents the total energy, total work done by the system, maximum work possible from the system. And Gibbs energy change at constant pressure and temperature gives you the non-mechanical external work, maximum non-mechanical work or non-expansion work that you can get. So now if you do at constant pressure temperature, you see that expression is this much. So this is basically what? This is basically the non-expansion work that happens due to change in composition. If you if you do a composition change, then this represents the non-mechanical or non-expansion compression, non-expansion work that it represents. Okay. So mu is this. What is mu? Is the chemical potential of a component in a homogeneous mixture, which is equal to rate of change of Gibbs energy change with respect to the particular species composition, with respect to the amount of that species in the mixture at constant pressure, temperature, and composition of all the other constituents. So this is the definition of chemical potential. Okay. Rate of change of Gibbs energy with the composition of that particular species in a mixture at constant pressure, temperature, and the constituents of others. Composition of other constituents. Okay. So this is chemical potential. Now, if you take a pure substance, then we know that G can be written as N into Gm. Gm is the molar Gibbs energy. Suppose per mole Gibbs energy is this. Then if you have n number of mole, then you can simply write it down N into Gm because this is extensive property. So for a pure substance, G can be written as Ngm. So therefore, it is actually Gm. So chemical potential for a pure substance is nothing but the Gibbs energy change per mole or the Gibbs energy per mole of that particular species. Okay. So molar Gibbs energy, that is basically the chemical potential for for a pure substance if you have. Now the next interesting question is, I think, see, these expression of chemical potentials are most commonly used. Okay. Del G del N at constant PT and N. How Gibbs energy changes with composition. But is this the only way you can define chemical potential? Okay, we normally in the book and all, you will see the chemical potential means this one, but that is actually not true. Okay, see here I have showed you, say for example, G equal to A, you can write it down in different forms, this energy changes. So G is like this, H minus Ts, U plus Pv minus Ts from definition. So what is U now? U can P minus Pv plus Ts. From here I can write down U equal to this. Now I write complete change in U, du equal to, simply I write all this. Okay. So what I'm writing now down, now dg we know, dg equal to vdp minus hdp is all term. So I bring in that. So the openness comes into here. I replace dg by this expression. Now you see all these vdp and sdt, they get cancelled. So I get this expression. Now from here I can write down, define mu again. How? Rate of change of internal energy with respect to composition at constant entropy and volume. If I take constant entropy, constant volume, then these two terms become 0. Then du becomes actually mu dni. Okay. So therefore, under what condition? Del u del n at constant s and v and nj. That is mu I. Okay. Earlier we showed del g del n at constant pressure temperature. So you see, it is not that this is the only one definition of mu. You can write the in this way also. You can write it in terms of other extensive properties. Say internal energy. Only thing is that the conditions are different. If you want to measure chemical potential with respect to internal energy, now the conditions are internal energy change at constant entropy and volume. Okay, and other compositions anyway. Similarly, it can be shown that you can write down mu in this way also. With respect to Helmholtz energy, if you want to write, then it will be again change in Helmholtz energy per unit mole of the species, but now it will be C at different condition, constant entropy and constant pressure. You can also write it down in terms of Helmholtz energy. Okay, this was for enthalpy, this is with Helmholtz energy. Again, here you see the conditions are different, temperature, volume, and then composition. Okay, so this, what you should remember, that this is not the only way. You can actually write down chemical potential as the effect of composition on any extensive property of the system. Okay, provided you maintain the right conditions. So instead of, if you write in terms of internal energy, then this is the definition. In terms of your enthalpy, this is the definition. In terms of Helmholtz energy, this is the definition. Gibbs energy, this is the definition. Okay, so this shows different extensive properties, how they depend on composition. Chemical potential shows that. Okay, how different extensive thermodynamic properties, these are extensive properties, U, H, G, A, how they depend on composition. Okay, chemical potential is a measure of that. How these different extensive properties change with composition. Only under different conditions, the conditions are different. So that you have to remember. Okay. So I think I will stop here today, because I wanted to just define open system, so that in the next class we will discuss a little bit more corresponding guiding equations of open systems, and then we will continue further. Subsequent to all the discussions, whatever classes we have, we will be dealing with open system. So compositions will change. Okay. So, and we will bring thermodynamic equations, and then so 1 or 2 applications. Say phase equilibrium or chemical equilibrium, we will talk about that in the next following classes. Okay, so I will first come out of this.